Welcome to LIB Academy. In this video, I'm going to take you through one of these electrocyclic reactions called Sigmatropic rearrangement. It's a rearrangement. Tropos from the Greek word means change, right? It means change. And sigma, tropos, simply means sigma change, right? So in this reaction, a sigma bond is going to be destroyed and reintroduced, in another place, right? So it's just a rearrangement. So the system is going to rearrange itself to form a new sigma bond by destroying an old sigma bond. So that's it for sigmatropic rearrangements. So I have a video on electrocyclic um, reactions too. You can also check that. Also a video on frontier molecular orbital theory, which is the first before coming to learn these things, which will help in predicting our stereochemistry of our products. This video is basically for sigmatropic rearrangement. So now let's continue. This reaction, like I said earlier, involve the breaking of old sigma bond and forming a new sigma bond, and every atom breaking and forming a bond without disobeying the octet rule. And we also have numerical notations that will indicate, the distance between where the bond is breaking, where the bond is broken and where the bond is formed. We are going to look at all these. So let's start a typical example. So we have this molecule here. So under sigmatropic rearrangement, like we said earlier, the localized pi electron system will rearrange themselves, right? So we are going to get this. If this pi electron should move to this place, then this one will also shift to that place, and then this one is going to come here. You see, we don't have any pi electrons here. It's just this sigma bond moving to reform here. So at the end of the day, this sigma bond is going to be destroyed and reintroduced here. I hope that is clear. So we have a pi electrons here moving to form a double bond here, and this one also moving to form a double bond here, and this one breaking to reform itself again. And don't forget, we have a methyl group here. So to draw this, you have to be very careful. So we have a double bond here. This one is no more there. So we have a double bond here, and then we have something like this. And there is a methyl group here too. We have a methyl group here. Just look at the reaction very careful. If you know what you are doing, then like if you know what the reaction is about, sigmatropic, you know that sigma bond is going to break and reform, right? So let's go. Drawing this, then we are here is going to be a single bond, and then here, since this one form another bond here, so this means this is going to be a double bond, right? So and then we go this way again. So I just want, there was a hydrogen here, so we are going to get a hydrogen here too again. Chair, we have numerical notation like this, which indicate where bond is broken and where bond was formed. Where we broke our old, sigma bond, and where the new one is formed. So for now, we could see that this was a sigma bond that we destroyed, right? And you could see that when we start numbering from this side, we're going to get 1, 2, we are numbering our carbon, 3, 4, 5, right? So this is where we broke our bond. So we broke this bond. So we also start numbering from the other side to where the bond was broken. So 1, do we have another carbon to number again? No. So this is going to be a 1,5 sigma tropic rearrangement. So 1,5 sigma tropic rearrangement. And these reactions occurs at elevated temperature. The examples of these reactions are the Cope's rearrangement and then Claisen rearrangement, which we'll be looking at them very soon. So now let's look at Cope's rearrangement. So for this one, at elevated temperature, mostly 200 degrees Celsius, this reaction can proceed. Generally 200 degrees Celsius, this reaction can proceed. And we know what is happening in Sigmatropic rearrangement. So we know that because of our delocalized electron system, we are going to get something like our electrons moving. This will move to that side. If you want to know how our delocalized systems look like, you can watch, the frontier molecular orbital theory, or just find a way of understanding the frontier molecular orbital theory. I also have a video on it. So it's going to show how the localized systems looks like. So when this moves to this side, we are going to get this sigma bond here destroying to form a double bond here, and this one will move here to form a bond here, right? Good. So looking at this, where did we break our sigma bond? We broke our sigma bond at this side, right? So this is where our sigma bond broke. So you could see that we are going to get something like, let's see, we have something like this. This bond moves to the side to form a double bond, right? And this one was broken to form a double bond here. So we are going to get a gap here, right? So after that, what next? We then continue with the rest of the how to from this. So this, we join this, um and that here, giving us something like this, right? So but don't forget, we have substituents here, methyls group here, so they are just going to join the molecules like it. The product like that. So the problem is, in what reaction is this? Is it Sigmatropic? And you should know the definition for Sigmatropic, that our pi bonds are going to be like, they are going to be the same, just that we are going to have our sigma bond breaking and forming somewhere. So you see that this sigma bond broke, right? And at the end of the round, it's reformed here, right? So just like that. Unlike the electrocyclic reactions, where we are using one pi bond to form a sigma bond. So in this case, we want to name this, what type of sigmatropic rearrangement is it? We know it's Cope's rearrangement, but what type of Cope's rearrangement is this? So this is where we broke our sigma bond. So let's start numbering there. 1, 2, 3, right? And numbering from the other side to 1, 2, 3. So that at the end of the day, this is a 3, 3 sigmatropic Cope's rearrangement, right? So you can follow this procedure by writing the product for, or predicting the product for any reactions under sigmatropic rearrangements. So let's look at number 2. What is going to happen? So if this will move this way, mind you, you can also start from this place, this moving to that, and this moving to this place, and this one moving to this side, and this one moving to this side. At the end of the day, you are going to get the same results. And we said this reaction takes place under elevated temperature. So if these electrons will move to the side, and this sigma bond is going to break to form a double bond here, and this one will break to form a bond here. So at the end of the day, we are going to get something like this. Yes, because when this one moves here, we are forming a double bond here and forming a double bond here. You could get something like this and something like this. So this will be our product. So using this same procedure, you can write the product. So again, what type of Cope's rearrangement is this? So we number to where we broke our sigma bond, right? From both sides. So 1, 2, 3. This is the bond that was broken. So 1, 2, 3. So again, this is a 3, 3 sigmatropic Cope's rearrangement, right? So I think that is okay. Let's look at Claisen rearrangement. But mind you, we are getting the same product as the reactant, just that the arrangement changed. the arrangement changes, right? So if you look at this reactant here, it's just the same as, basically the same as this product, but just that the arrangement of the atoms changed. And looking at this reaction to, just the same, by the arrangement changes. So let's look at Classen's rearrangement. For Classen's rearrangement, it's just the same thing, but in this case, we have the molecule containing an oxygen, right? We have the molecule containing an oxygen, and this one can be divided into two, where we have an allylic and vinyl group, and in the presence of the oxygen, we can also have an allylic phenyl group, and in the presence of oxygen. So what we are going to do is that for this reaction, you can see that we have a vinyl group here, a vinyl group here, a vinyl. Why a vinyl? We have two carbon groups with a double bond between, right? With a double bond, yeah, two carbons with a double bond. So we have one carbon here, one carbon here with a double bond. So this is a vinyl group. This functional group is also an ether, right? So if you see vinyl ether, and we also have an allyl group, we have three carbon units with a double bond between carbon 2 and carbon 3. So if we are to number this carbon 1, 2, 3, 3 carbons, if and 2 with a double bond between 2 and 3. So 3 carbons with a double bond between 2 and 3. This is an allyl group, right? So this reaction is going to give us a certain product, and it will favor the formation of um, oxygen carbon double bond, which is stable as compared to this. So like I said earlier, it's just the same, just that we have oxygen in this case. So this double bond moving to this side, and then we have this one moving here, and this one moving to that place, right? So looking at this molecule very carefully, you could see that we form a double bond oxygen here. So double bond, carbon double bond oxygen here. Then after that, we have this coming. So we have something like this. Then after that, we have this new bond here, and then followed by this one here, and then this one right here, and then our methyl group, right? So you could see that when this one bond broke, it formed a double bond here, right? So we are going to get a double bond here. So you see this reaction will occur when this, in the presence of this molecule in space, there's a possibility that this one will react to form an oxygen carbon double bond, which is very stable as compared to this. So mostly for Claisen rearrangement, which involve ether, allyl, and vinyl group, there is usually favors the formation of oxygen carbon double bond. Sorry. Let's look at our number 2. So what is going to happen here? If this to move to this side, we're going to get our oxygen carbon double bond, and this bond will break to form a double bond here, and this one will move to form another bond here. So we are going to get a product which looks the same as this. So oxygen carbon double bond, then we have this carbon right here, then we have this one here, then we have this here, and then that. But mind you, we formed a double bond here, so a double bond should be here. It's just the same as this, just that this time we don't have a substituent here. So now that we look at the cleansing rearrangement, where we have an allylic system and allyl and vinyl, right? And we know that for our ether, it always there, because like it's generally there, because we have we know that for cleansing rearrangement, oxygen is added to, we can find oxygen in the molecule. So now let's look at vinyl, allelic system, allelic phenyl ether system. So we have a phenyl group, and this is our phenyl. Phenyl, and our allelic part is this. Allelic part is this allelic. So this reaction, mostly when you see generally, if you see a phenyl group in the present, like a phenyl group and an allelic system, definitely the reaction is going to, the product that we get will tautomerize to form alcohol as a product. Phenol as a product, phenol product. So let's start moving our electrons. So the problem is going to start where we have. So if we get a molecule like this in space, there is a possibility that they will arrange in this form, and this electron here will move to try to form a bond here, right? And when this moves to this side, this one also move. So when one move, everybody moves, like, and then this one also move. It depends for you to see clearly. So how are we going to write our product for this? Firstly, let's see where the oxygen carbon double bond is formed. You could see that this moved here. There is carbon oxygen double bond is going to form here. So let's draw our final. Oh, this is very bad. You know that our oxygen carbon double bond is formed right here, just here. And what remains is we have this new bond forming here. So new bond forming here. So we are going to get a new bond here, and another one, and another one, right? So where this one is a single bond, this pi electron move to form a double bond here. So just like that. So that is our product. Then this equilibrium formation, like this equilibrium formation, and favors the carbon double bond formation, the carbon double bond. So this occurs to form carbon double bond. And since we have phenyl group in an allelic, there's going to be a tautomerization to form a very stable alcohol. So this one can react further to form a more stable alcohol than this. So when this one tautomerizes, we're going to get something like this. Alcohol group, and then that's, so this will be our final product for this reaction. Then again, what type of Claisen rearrangement is this? Mind you, you can name the type by following the same procedure, right? Like looking at where our bond breaking and our bond formation, like, see, we start here, and this is where our new bond is formed. We see that this is where our new bond is formed. So we start numbering from this side and from that side. So you can see that we have 1 here, 2 here, and then is that 2, 3, right? And this one is going to start here 1, 2. What's happening? I've already named this one, right? So one should start here 1, 2, 3, right? So 1, 2, 3, 1, 2, 3. This is where our double bond was formed, which means we have a carbon here, right? So this again is a 3-3 Sigmatropic Claisen rearrangement. So thank you for watching. To keep me going, kindly like this video and probably share or comment below. Thank you for watching. And don't forget, I have videos on other reactions too. You can check them out.